Surendra Rekar for his kind invitation. Thank you very much. My presentation is entitled Conductive Multifunctional Concrete. It is widely known that the main function of concrete is its structural function. On the other hand, concrete is a bad conductor of electricity, it's a dielectric. However, the addition of a conductive carbonaceous material such as graphite products, carbon fibers, carbon nanofibers, carbon nanotubes, transforms the resulting mixture into a conductive materials. And this gives the possibility of using this new material for other function different from the structural one. So it can be considered a multifunctional materials. Possible applications include sensing function, heating and de-icing function, and electrochemical application. Here we can observe some pictures of cement-based materials and some carbon fibers and carbon nanofibers. In first place, let me comment on the first function, that is the sensing function, or the ability of a structural material for detecting its own deformation when subjected to some external static or vibrating load. This means that we are in the presence of a very promising and interesting material if we want to plan an intelligent structure. Specific applications include structural vibration control, traffic monitoring, building safety, AC optimization, and structural service monitoring. Sensing function is based on the change in the electrical resistance in concrete when some stress is applied to it, and it is quantified by the gauge factor, that is the ratio of fractional change in resistance divided by the fractional change in the formation. Due to the change in dimension, length of sections not being significant, then the change in resistance must be due to the resistivity change in this material, and that is a material intrinsic property. Let me explain this figure. The material strain sensing capacity is defined as the response on the volumetric electrical resistivity, proportional and reversible, and due to its strain state. If a longitudinal compressive stress is applied, the electrical resistance in that direction is reduced. The contact between fibers themselves and fibers and paste becomes closer and closer, and consequently the contact resistance also changes. And vice versa, the material recovers the initial state when the stress is removed. Both effects are reversible in the material's elastic range. Therefore, the electrical resistance returns to its initial value once the load is removed. It is an important figure. You can observe that we are working within the elastic regime because stress and strain are reversible. When the load is initiated and the stress increases, the deformation also increases, shown in blue. And as a consequence, a proportional decreasing of the electrical resistance can be observed, shown in the low. After this first loading step, the load is returned to zero, and so stress and deformation recover the initial value, as well as the electrical resistance or electrical resistivity. It is important to calibrate each and every sensor previously to its application. To do so, the slope of the variation of resistivity versus deformation gives us the so-called gauge factor, which controls the accuracy of the measurement. In order to know the limits of the carbonaceous additions, it is important to know the value of the property called percolation threshold. Percolation threshold comes when there are enough fiber density to establish a continuous path of electrical current. For a given slenderness, increased carbon fiber content decreases the resistivity. Once the percolation threshold is reached, it makes no sense to increase the percentage of carbon fiber because the resistivity is not any more significantly changed. On the other hand, as the fiber aspect ratio increased, percolation was achieved at lower carbon fibers content. This graph validates the sensing function. This figure shows the result of a test still in the elastic range, which loads were increased and maintained for 60 seconds before the next load step and then symmetrically decrease. Again, a very good response was observed, even in constant. In blue, the strain monitored with a strain gauge, and in red, the resistivity of the specimen. Once more, proportionality between electrical and mechanical parameters, as well as reversibility, can be observed. This is another important graph. In this slide, the response for loads surpassing the material elastic limit is presented. That is, the material is behaving in the plastic state, and the strain is not longer proportional to the stress. The initial strain is not recoverable with the initial load. Similar behavior can be observed with electrical resistant chains, probably because of the decoupling and breaking of carbon fiber in cement matrix. Therefore, that means that damage can be controlled while monitoring the electrical behavior of the sensor. Next, we decided to check the viability of attaching a small specimen of conductive cement paste on the surface of the standard concrete specimen, not conductive. On the left hand, we can observe that two different gauges were used, one of them attached to the concrete specimen and the other on the conductive specimen. That way, we could control the strain of both elements. On the right side, we can observe the electrical resistance change in the small control specimen and the strain in the concrete. So by controlling the resistance of the attached sensor, the deformation of the standard concrete specimen is monitored. After this study with sensor attached to a small concrete specimen, we decided to attach them to a regular side reinforced concrete beam, and 28 cement composite sensors were prepared. Two different tests were made depending on the magnitude of the maximum strain and stress in the reinforced concrete. The first one remaining the beam in the elastic regime, and the second one producing cracking and final breaking of the beam. This figure shows the results of the one test with different loads and unload status for an on-site fabricated carbon sensor on the upper side, complicit phase of the beam. In the red sensor beam strain in micro deformation, in blue the electrical resistance of the sensor, both versus time. Very good response was observed again. Our final goal is to reserve conductive cement-based materials which are capable of being strain sensors and can be applied to real structure elements for structural heat monitoring. Our future research effort focused on a measurement system that can be computerized and a control algorithm implemented in a real structure in order to have real-time feedback of strain that can be used for structural health monitoring. The next function is heating and de-icing function. Many methods and techniques have been investigated for pavement anti-icing and de-icing, as snow and ice on roads causes enormous losses in human lives, infrastructure and materials. The mechanical snow removal technique is the most used, but it is an intensive, expensive and time-consuming labor. Furthermore, not all the snow is completely cleaned from the driveway by snow plows, leaving a small layer to be eliminated. Many methods currently used to remove ice from roads are based on the use of chemicals. Most of them are harmful to both reinforced concrete and steel structure, viaducts, tunnels, airport runways, and for the environment. Compared to these methods discussed, there is the possibility of using heating system of conductive concrete layers. Addition of a conductive carbonation material to cement-based material allows to reduce the electrical resistance of the resulting material, so that application of the potential difference produces an electrical current by Joule effect, which is able to quickly melt the ice deposited, so it can be considered as a curative process, or to prevent its formation from the freezing of the mixture on the roadway, so it can be considered a preventive process. As it is well known, Joule effect is based on the thermal effect produced by electrical current through conductive base. Well, heating test consisted of applying a constant voltage between two ends of sides of each specimen. Cement paste with different carbon addition were prepared in order to study their heating capacity. Different tests were carried out for each sample, varying the applied voltage. In this figure, the average temperature for all PT100 sensor and power supplied versus time is shown. In this figure, we can observe that when the power is turned off, yellow line, then the temperature starting from around 24 Celsius degrees in red line increases slightly to reach a constant value around 42 Celsius degrees. Then, once the power is turned off, the temperature decreases up to the room temperature. We have also developed other tests reaching lower and much higher temperatures, even up to 140 Celsius degrees, of course, depending on the composite and the power applied. In any case, we are only interested in action against icing. In this stage, we considered to validate the mechanism of heating and to check that heating is produced by Joule effect. The process will be divided into two stages for which the mathematical equation that govern them will be defined, heating and cooling. The first stage is the stage of heating produced by the application of the electrical current. The sample is heated by Joule effect in a non-steady process, and changes of thermal energy in the sample are due to the applied electrical power minus the rate of the energy lost by cooling, which can be calculated with the Newton's law of cooling. In the second stage, the time lapsed is long enough so it implies a steady state and a constant temperature. On the other hand, the electric power supplied, in this case, is equal to the energy lost. Finally, the stage 3 is the stage of cooling. The sample is not electrically heated. In this case, thermal energy of the sample is released to the outside. In this figure, we can observe the experimental results and the calculated results. In any case, the simplified model is an excellent tool to study the influence of the different parameters in the heating of the samples. Practical application is based on the feasibility of the use of cement-based material studied to control ice layers in transportation infrastructure. A thick layer of ice was added on both sides of the samples, and it is observed a great increase in the ice melting rate with the application of electrical power. In this figure, we can observe the evolution of the surface temperature of the specimen in one of these tests by thermographic imaging. Well, let us imagine a real situation in which an airport runway suffering a snowstorm, therefore with a temperature
under minus 10 degrees, and snow plows are removing the snow, and indeed the airport is suffering a real problem of flight management. And let us imagine again that the upper layer of concrete of airport runway is a conductive layer, and then a power supply is turned on. As a consequence, the average temperature of the surface could be increased above 0 degrees. Well, we tried to transform this idea in experimental research. The specimen was introduced into the freezer, being the temperature of the freezer in minus 15 degrees. Then the power supply was switched on, and as a consequence, the temperature of the surface of our specimen increased, reaching temperature above of 0 Celsius degrees. Many hours later, we switch off the power supply, and as a consequence, the temperature of the specimen reached the same temperature of the ambient. This is, without doubt, a curative test. And now let us imagine an airport in a real situation of fine weather, and suddenly the same snowstorm as before. Temperature is decreasing rapidly, reaching an average temperature of the surface of 5 Celsius degrees. And in this case, the experimental test that we call prevention test, the specimen at room temperature were introduced in the freezer. When they reach approximately 5 Celsius degrees, power source was connected at a fixed voltage. After steady temperature was reached, then power source were turned off. Well, the main goal of this function is the development of the heating and the icing function in pavements such as airport runways. Instead of heating the whole depth of an airport runway slab, the heating is applied to a conductive layer with a formulation compatible with the slab concrete and oily some centimeters deep. Next, I am going to present you the electrochemical application function. The principal objective of this function is to study the viability of the application of a conductive cement paste as an anode in the application of these electrochemical techniques, such as electrochemical chloride extraction and cathodic protection. The corrosion processes of the steel reinforcements embedded in concrete are the main pathology affecting the durability of reinforced concrete structure. It is well known. Corrosion starts as a consequence of the destruction of the passive film, which prevents the steel to corrode. The main causes are the carbonation of the concrete cover in urban environments, or the presence of certain amount of aggressive ions such as chlorides in seaside environments, or due to the use of the icing salts. European standard limits its content to 0.4% of cement mass. When corrosion occurs, it is necessary to repair the structure if we want to use it for more time. Otherwise, there is a high risk of collapse. The traditional method for a structure contaminated by chloride is the replacement of the structural elements affected by the corrosion process. However, there exist some new methods such as cathodic protection, electrochemical realkalization, or electrochemical